So, you be in the AI space of things, you're probably very familiar with like the latest wave of like foundation model for GitHub Copilot or DALL-E 2, right? There's generate a lot of interest in the type of model that can combine more than one modality, like such as like vision and language in general. And so these sort of hybrid vision and language models have demonstrated a lot of impressive capabilities in a variety of like challenging tasks, like image captioning, code generation, and visual question answering. And then for us at Collabs, we have seen like a new paradigm of video foundation model that can learn from video data using some of the principles from this type of foundation model. And so in this presentation, I will give an overview of how the kind of history of how this new paradigm has evolved. I'll start out exploring the architecture of foundation model, namely speaking, the training and fine-tuning paradigm, as well as the concept of scaling laws. Then I'll talk about how the vision and language model can combine the power of both computer vision and NLP, and how they are currently being used to solve complex problems. And then finally, I will examine how video foundation model currently bringing a new revolution to the understanding and analysis of video data. So with that, a quick definition of how what is foundation model, right? So it's a type of machine learning model that can learn a wide range of data using self-supervision at scale. So the idea here is want to create a model that can be used for many different tasks. And by training on a lot of data, this model can learn the general patterns in the data. And when the model is used for a specific task downstream, it can use this knowledge to quickly adapt to the task. And at the backbone, foundation models use deep neural networks and self-supervised learning. And both of these two concepts has been popular for like almost a decade now. And some of the recent improvements in both of these areas have allowed for the creation of larger and more complex model. And these models are trained on massive amounts of data, often without explicit labels, right? So the result is that the model can learn a wide range of patterns and relationships, which can be used for many tasks. Like you see here on the slide, like using like text, image, speech, it can adapt to like question answering, info retrieval, analysis of the sentiment, object recognition, and much more. And that had led to significant improvement in processing of languages of vision, audio, and even multimodal AI, right? And from a practitioner point of view, if you can create one model that can be used for many tasks, then you can save a lot of time and resources and speed up progress in many fields. And the picture on the right side is an example of some of the latest sort of models coming from big tech and startup that have come out like in the past like few months, right? So you have like everyone know about like GPT-4 and Palm 2 and Llama, but there's also like Claude and from Anthropic, DALL-E from Databricks, Red Pajama from Together, and the MPT model family from ML, just to name a few. So I kind of want to go deeper into kind of history of some of this concept, and kind of take a step back and talk about this concept of transfer learning first. So traditional machine learning, typically trained from scratch, and so that requires a lot of domain-specific label data set in order to perform well, right? If you only have a small amount of data, then you actually can leverage the benefit of transfer learning. So that this idea here is you can take the knowledge learned from one task and then apply it to another task, so that you don't require as much data as you could if you were to train from scratch. And then for deep neural networks, pre-training is the dominant approach to transfer learning. So you train the model on an original task, and then you fine-tune it to another downstream task of interest. And we've been doing, this technique in computer vision since the 2012, 2014 era. Typically, you train a model on the famous ImageNet dataset, and then you keep most of the layers, and then you probably gonna replace the top, top 2 or top 3 layers with newly learned weights of the downstream task, right? Alternatively, you can fine-tune the model end-to-end. And some of the most popular pre-trained models for computer vision tasks include, AlexNet, MobileNet, Inception, EfficientNet, and YOLO. So for language, initially pre-training was limited to only the first step, which is what we call word embeddings. So if you think about it, like the input to a language model is words, right? So one way to encode them as a vector is through a very simple technique called one-hot encoding. So given a large matrix words, you know, as you see on the left side of the screen, you create an embeddings matrix and embed each word into a real value vector space. And so this new matrix, which after one-hot encoded, it's a reduced dimension on the order, maybe even 1,000 magnitude compared to the original version of it, right? And perhaps some of those reduced dimension correspond to some sense of semantic notion. So back in 2013, there's this very famous research work called Word2Vec, and it did exactly this. And it looked at which words frequently co-occur together. And the learning objective here is to maximize the cosine similarities between different, word embeddings. And as a result of that, Word2Vec can perform pretty cool, like vector map, basically on these kind of embeddings. So, for example, when you embed the word, the three words king, man, and woman, you can do vector map to get a vector that is close to the word queen in this embedding space. And so, with some of these, discovery, it is quite useful to see more context to correctly embed words, because this word can play different roles in a sentence depending on the context. And if you do this, you can improve accuracy on all the downstream tasks. So in 2017, 2018, a couple of models like Elmo, LLM-Fit, and the original GPT model have empirically demonstrate how language modeling can be used for pre-training. And more specifically, all these three models employ pre-trained language model to achieve state-of-the-art results on a diverse range of tasks in NLP, including things like text classification, question answering, natural language inference, co-reference resolution, sequence labeling, and many other things. So this is sort of like the original part of how people started realizing how important it is to pre-train Georgia model on text and then perform it for the task that apply. And what really sort of kickstart this whole revolution is architecture that you probably very well aware of. So Transformer come from a 2017 paper called Attention is All You Need. And before the introduction of this architecture, the state of the art in NLP was based mostly on either recurrent neural networks or sequence to sequence architecture. And then both of these kind of family of architecture, they process the data sequentially, meaning that they look at one word at a time in the order that words appear. So the innovation of Transformer is that it can parallelize language processing, meaning that it allows all the tokens in a given body of text to be analyzed simultaneously rather than in sequence. And in order to do that, Transformer relies on a mechanism known as attention to support this parallelization. So attention enables the model to consider the relationships between words, even if they are very far apart in the text, and that help determine which words and phrases in the passage are most important to pay attention to. And then consequentially, parallelization also makes Transformer much more computationally efficient than recurrent neural networks, allow them to be trained on a larger data set and view with more parameters. And a lot of the modern day Transformer variants, which I will talk about in the upcoming slide, have a common character, which is common, characterized by their massive size in terms of both the architecture parameters, but also in terms of the data set that was trained on. So in the domain of computer vision, probably convolutional neural network has been the dominant architecture in the past decade or so. But given the success of Transformer in NLP, a lot of the vision researchers start looking at way to adapt this architecture to visual data. And so this paper, I think around 2021 from Google introduced this notion called the vision transformer, and it applies the encoder block of the transformer architecture to an image classification problem. And namely speaking, the author of this work split an image into patch and then provide the sequence of linear embeddings of this patch as input to a transformer. And then similar to this concept of token in an NLP setting, you can think of this image patch as the input, to the model. And regarding the architecture itself, it included a stem over here that patch the image, a body that is based on the multi-layer transformer encoder. And then on top, it got an MLP, a multi-layer perceptron head that can transform, this whole global representation into the corresponding output label, right? So, with this new technique, a vision transformer either, exceeds state-of-the-art results on many image classification dataset, while being quite relatively inexpensive to pre-train. And although, vision transformers show a lot of potential, they do actually indeed have some problem. And significant issue is that they have some difficulty with higher resolution image because they require a lot of compute power to pre-train. And that also increased rapidly with the image size, right, of the data set. And additionally, because vision transformer has a fixed scale token, sometimes it's not quite useful for any task that require dealing with any visual elements of varying size, like video, for instance. Now, there's a flurry of research that follow the original transformer architecture, and most of them made some enhancement to that architecture in order to address some of the shortcomings that I just mentioned. So here in this slide, I included 2 variants that is worth paying attention to. So in 2021, Microsoft published this work called Swing Transformer, which essentially a generic transformer architecture that can be applied to any type of modality. And the Swing Transformer included 2 major concepts, hierarchical feature maps, and then shifted window attention. So this model used hierarchical feature maps to enable advanced techniques for dense prediction, meaning like you want to predict, any concept that have a lot of visual elements, right? Like the analysis. And it can also achieve linear computational complexity by computing the cell attention locally within non-overlapping window that partition an image. So as a result of that, a lot of folks start using Swing Transformer as a good backbone architecture for a variety of computer vision tasks. And then shifted window means that you bridge the window of the preceding layer of your architecture. So this strategy is quite efficient in terms of even like real world latency. So all query paths within a window want to share the same key set. And then that means it makes it easier for the model to access the memory in the hardware, right? So like, I can think about compute time, and if you do a real engineering problem, they could be very, very powerful in that context. The other work I want to mention is called Perceiver. So this is another variant of the transformer created by the team of DeepMind, and it took a lot of inspiration from biology, actually. So at a high level, the Perceiver can, follow the same attention-based principle to process a variety of input, including things like image, videos, audio, and even like very like bizarre data type like point cloud, for instance. And it can also handle a combination of different types of input without relying on any specific assumption about the domain. So 2 major things I want to point out to about the Perceiver architecture. It introduced a small set of latent units in order to form an attention bottleneck, and it helps with eliminating the problem of O-to-O attention, and allows for a very deep model, meaning models with like a lot of building blocks, right? And as a result of that, it can attend to the most relevant input that was informed by the previous steps. However, like in a lot of the multimodal context, it is important to distinguish the input from one modality to another modality, right? You want to distinguish between like, to say, text with vision, right? So in order to do that, the Perceiver associate position specific and modality specific features with every input element. And as a result of that, it can like compete, that's this distinction, right? Let's say between text or vision. Yeah, so those are some of the variants that I wanted to talk about. And that has been quite powerful, that sort of informed a lot of the work for vision and video that I would go over in the upcoming few slides. And so for the second part of the presentation, I want to talk about kind of all the work that came into following the original transform paper, starting with NLP domain, and a lot of people nowadays call it large language model, right? So GPT and GPT-2 came out in 2018 and 2019, respectively. And that the name stands for Generative Retrained Transformer. These are decoder-only models, and they use this concept called mass self-attention. And concretely, that means like, at a point in the output sentence, you can only attend to 2 input sequence vectors that came directly before that point in the sequence. And then why the GPT embeddings can also be used for, classification and, prediction, etc. GPT is probably most well known for it work in, today's most well known large language model, the ChatGPT, which is actually the task of prediction, right? You predict the next word in the token, like the training set that it was, being trained on. The original, GPT and GPT-2 model, they were trained on 8 million web pages. The largest model has about 1.5 billion parameters. And the task that the GPT-2 was trained on is predicting the next word in all this text on the web. And the author found that, it works increasingly well with an increasing number of parameters. So around the same time, Google released this paper called BERT, which stands for Bidirectional Encoder Representation for Transformer. So BERT is an encoder-only transformer designed for predictive modeling, and it introduced this concept called mass language modeling. So during training, BERT must are random words in a sequence and has to predict whatever the mass word is. And with that sort of training paradigm, it become more robust, and for scenario where it doesn't know like what to predict, right? And regarding the size, BERT has about 110 million parameters. And then finally, in 2020, Google released this work called T5, which stands for text-to-text transformer. So T5 has an encoder-decoder architecture. It was trained on the C4 dataset, which is about 100 times larger than Wikipedia. And it has around 10 billion parameters, which is, put that in context, it's like almost 10 times the size of GPT-2, right? So as you can see, like every year, like people start thinking about ways to increase the size of the model, and what eventually became what we know as scaling law. So at a high level, scaling laws predict continuing improvement in model quality as we continue to scale up the computational budget, and that can mean bigger model, or it can mean like more training data, right? So in 2020, the team at OpenAI investigate the scaling laws, and they show that scaling laws are very predictive of the future performance. Empirically speaking, their experiment revealed that the test loss of the model training after the training process follows a power law with respect to the model size, the dataset size, and the compute used for training, like sometimes spanning over like orders of magnitude. And this suggests that the relationship between these 3 variables can be simply described by the equation that I put here on the slide. And that can help with optimize training configuration of large language model. And additionally, the experiment indicate that some of the other architectural details, like if you do things like opening up the network depth or like increase the width, they will have like minimal effects, within the scheme of thing, right? And so based on the experiment and the equation shown, in the slide, they found that larger model are significantly more sample efficient. And in other words, some of the optimal compute efficient training requires training very large model on a relatively modest amount of data, and stopping significantly before conversion. So since the publication of that scaling laws paper, there's been even more interest in way to like scaling up this language model, right? So in 2020, OpenAI released GPT-3, and this work, you know, in terms of the size of the model, is actually 100 times larger than GPT and GPT-2, right? Like, let's say 175 billion parameters compared to like 13 and 1.3 billions. So due to that scale of the size, GPT-3 was able to exhibit like some of the capabilities that we have never seen before in a lot of like the few shot and zero shot learning tasks. In other words, like the more examples you give the model, the better its performance will be. And then the larger the model, the better its performance will get. And put it in an empirical lens, the team over at Google publishes work, quite an important work called Emergence Abilities of Large Language Model. And it explores some of these, you know, emergence abilities. Yeah, that was present in larger model, but not in the smaller model, right? The paper examines some of the research that analyzed the influence of the scale of comparing models of different size trained on varying computational resources. And they found that like for a variety of tasks, the behavior of the model, sometimes they search unpredictably from random performance to above random at a very specific scale threshold. But for instance, like if you have more than 70 billion parameters, then it will suddenly like perform like extremely well and some form of task, right? So in 2022, DeepMind proposed this work called Training Compute Optimal Large Language Model, and they code the chinchilla scaling laws. And this is actually a more accurate scaling law formulas than the original one proposed by OpenAI. They train over 400 language model with you know, a wide range of parameter size from 70 million to 16 billion on another wide range of, you know, tokens data set from 5 billion to 500 billion token. They predict the optimal amount of data given the number of model parameters, and they found that, you know, most of the, you know, large language model at the time was undertrained, meaning that they haven't seen enough data, right, in order to get good performance. So to verify this, they trained another large model called Golfer, and Golfer had about 280 billion parameters, and it was trained on 300 billion tokens. And then Chinchilla is only 70 billion, right? But they increased the size of the data set that Chinchilla was trained to 1.4 trillion token, which is like 4 times the size that Golfer was trained on. And they found that like despite Chinchilla has like significantly smaller parameter size, it actually exceeds the performance of Golfer. So this suggests that the model size and training tokens are equally important when you're training large model. And since the formal and empirical analysis of the scaling laws, many of the modern day language model have been released. You know, I include on the slide in the introduction about that, but at a high level, like this model achieve a lot of, you know, state-of-the-art few shot results on different tasks simply by scaling the model size, by using some specific like activated module that can perform sparse attention, and by, you know, training on data set from even more diverse sources. And some of the notable examples here include Megatron LLM, which has about 8.3 billion parameters, GLAM, 64 billion parameters, original Lambda from Google has about 137 billion parameters, Megatron Turing NLG, 530 billion parameters, and then lately there's a model called Palm by Google, 540 billion parameters. So you can see like it keep increasing in size. So I talk a lot about like kind of scaling laws in the vision, in the language domain, but there's also been work that actually look at like the effect in the vision domain as well. So this work coming from the team at Google back in 2022 shows that the scaling laws also apply to computer vision tasks. So they conduct an experiment with the vision transformer models, and they look at the model with just maybe like 5 million to like 2 billion parameters, and they train it on data set that range from 1 million to 3 billion training images. And they also have like, wide range of compute budget as well, from like very small TPU to like 10,000, TPUs, for instance. And the big takeaway out here is that they found that simultaneously scaling the total compute and the model size is effective, right? And the most optimal approach is when you increase the size of the model with available additional compute. And for vision transformer specifically, if given enough, if given sufficient training data, they will follow the power law curve, meaning that larger model will perform better in future learning contexts. So thanks to the vision transformer architecture that I mentioned, there's been a lot of interest in models that can combine vision and language together, right? And we call them the hybrid large vision language model. And they can do a lot of things, from image captioning to image generation to like visual question answering. And at a high level, like this type of vision language model consists of 3 key elements: an image encoder, a text encoder, and a strategy to fuse the information from the 2 encoders together. So for the next few slides, I want to review some of the most well-known models in vision language research over the past 2 years or so. Probably the most popular one is called CLIP from OpenAI. So they come out in 2021, and CLIP stands for Contrastive Language Image Pre-training. So the input to CLIP is 400 million image to text pairs that were crawled from the internet. So CLIP encodes the text, encodes the text here using a vanilla transformer, and then it encodes the image using the vision transformer. And over here, it apply what they call contrastive learning in order to train the model. And at a high level, contrastive learning, they match the correct image and text pairs using cosine similarities. And so, with this powerful like pre-trained model, you can map in image and text using, embeddings essentially, even on unseen data. And there are 2 ways to do this. One way is that you can use a linear probe, and linear probe is when you train a simple logistic regression model on top of the features that the CLIP output after performing inference, right? And alternatively, you can use zero-shot prediction. And for that, you encode all the text labels and then compare them to the encoded image. So both approach work equally like decently, but I think in that work, they found that linear probing is slightly better, because you actually have that additional sort of prediction guardrails to make sure that the result is good enough. Like that means like the image and text are close enough in that embedding space. And I just want to clarify that CLIPs does not directly go from image to text, or like vice versa. They do that via embeddings. That means they convert like these modalities into embeddings, and they map that in the same like latent space. And as you can think of, like this embedding space is quite useful for performing retrieval and search across different modalities. So so following CLIP, there's a lot of work that kind of leverage this notion in order to do a variety of tasks. So this example is from Google, and it's called COCA, which stands for Contrastive Captioner. So this is a foundation model that combines contrastive learning with generative learning, and it uses an encoder decoder architecture that has been modified and trained with both contrastive loss and captioning loss. And as a result of that training paradigm, COCA can learn the global representation from unimodal image and text embedding, meaning that it learn just the knowledge of that modality, but at the same time, it can learn some of the like finer grain region level features from the multimodal embeddings, right? So you want to learn both the surface, but also like some of the final specific details that the 2 modalities have in conjunction with each other. And this work was was for an image captioning task, right? Like given an image, you want to provide the correct caption that describe what's happening in the visual scene. And in late 2022, the team over at DeepMind created a group of visual language model called Flamingo. And this type of model can do many different things, even with just a few examples of input and output. At a high level, Flamingo has two major components. They have a vision model that can understand visual scenes, and they have a language model that helps with reasoning. So the model uses depreciation and knowledge to work together. And Flamingo model can take as input very high quality image or video, because they leverage what an architecture called Perceiver, which I talked a little about in like a couple of slides ago, right? And Perceiver architecture can analyze a very large quantity of visual input features and then produce like a small number of visual tokens corresponding to that big input. And thanks to some of these architectural innovation, the family of Flamingo model can connect very strong pre-trained model for vision and for language, and can handle sequence of very mixed visual and text data, and can also use both image and videos as input. And the biggest version of the Flamingo model family is called Flamingo 80B, which meaning that they have 80 billion parameters, and it sets a narrow curve in different feature learning tasks that involve understanding language, image, and video altogether. So in the past, like a couple of months, you've probably seen like some big tech company release their own version of large vision language model. So I'll only highlight here 3 of them, but they do have like a ton more, right? So Microsoft released this work called Cosmos 1, and this is a multimodal language model that can perceive different modalities. And it can learn context and follow instruction. So Cosmos 1 can generate text based on the previous context and handles text and other modalities using a transformer-based causal language model. Cosmos was trained using different types of data and can perform well in different scenarios, include tasks like understanding and creating language, recognizing image, and answering questions based on images. Over here is the work called PaLM E by Google. And PaLM E is an embodied multimodal language model that can handle various reasoning tasks based on observation from different sources and using different embodiments, including like internet scale, language, vision, and visual language domain. The biggest version of PaLM E is called PaLM E 562B, meaning that it has 562 billion parameters, and it can reason about different things without being trained on beforehand. It can like tell jokes based on the image. It can do tasks in robotics, like talking, perceiving, and planning. Like if you watch the recent Google I/O keynote, I think last month, PaLM E, I think PaLM E 2 maybe like was released back then, and you can take a look at that more and to kind of go deeper into the details of the application of like Google PaLM E. And then the one that everyone was talking about, probably most popular, is GPT-4 by OpenAI. If you've seen the keynote from Greg Brockman, like he took a picture, right, of the of like a hand drawing sketch that he wrote down, and that fit into the OpenAI API that create like a full-fledged landing page website, right? So GPT-4 remote, like it is basically a large multimodal model that can process image and text input and produce text output, right? And here in this slide, I produced a sample chart of results from the paper, but it can, it performs super well on different exams, like law exam and like biology, Olympiad exam, right? So it shows pretty incredible capabilities in like, in tasks that human sometimes struggle with. So for the final part of the presentation, I want to talk about this new paradigm of video foundation model. So video understanding, it has become quite important lately. You've seen a lot of video content on social media platform. You've seen an increasing use of surveillance camera in public space, etc. Right? So there's more and more need to make sense and analyze this kind of video using some sort of automated video understanding automated video understanding system. Despite like the importance of this problem, though, like video understanding as a research problem has received like quite little attention compared to like text and image understanding tasks. And that is because there's a couple of major challenges that you think about when dealing with video. Number one is that, there's a high compute burden that requires when you process video. Video are much larger in size than text or image. And as a result of that, they require significantly more processing power for analysis, right? And this issue is even more amplified with the transformer architecture, and because it had a quadratic complexity with respect to token length, meaning that for every like token, like the overall compute needed is like 1 to the power of like 12. So that you can think of at that scale, like you add a lot of like compute for each of the token that you need to process, right? The second challenge is this issue with temporal modeling. So unlike text and image, videos contain a temporal dimension that must be taken into account when performing analysis on them. And as a result of that, it requires specialized techniques and the type of model that can perform like, time series, for instance, that are not commonly used in many of other modalities. And then finally, in addition to the visual and language information presented in the video clips, there's also synchronized audio cues that require additional processing. What I mean is that like these audio cues, it can be like, any sounds in the video frame, can be conversation between two people happening inside video, and they like correspond with like the visual element, right? Let's say if there's two people in the frame, you want to capture that image of two people speaking and the type of conversation that they were talking about, and synchronize, the visual and the sound/audio element. We call it like, visual audio alignment, right? It's actually quite challenging. And, it's very important to like take into account like these audio cues, because, they can provide some sort of important information about the video that cannot be found if you only look at the visual analysis or the text analysis, right? So yeah, these are the three major challenges. But obviously, like, there's a lot of work lately as well, to tackle some of these challenges, right? And there's an active research community focused on video understanding lately. And I want to highlight a couple of like the major work in the past like few years or so that has been like at the frontier to develop video understanding systems that are robust and reliable enough that can be used in real world application. So in 2019, Google introduced this work called VideoBird, which applied the BERT architecture that use self-supervision to video. So VideoBird has it leveraged three pre-existing methods: automatic speech recognition, vector quantization for spatial temporal visual features, and a BERT model for tokens sequencing. And then combining these three components together, it can model the relationships between the visual and the linguistic domain. And so to make BERT work with video, the author here, they turn the raw video data into visual words using vector quantization. And this helped the model to focus on the most important parts of the video and how, that changed over time, right? Like it only look at part where like they cut the cabbage. It only look at part when like they, add soy sauce, right? And then keep trying. So these are sort of the important part of the video that VideoBird look at. And as a result of that, VideoBird can outperform, a lot of other models in different video captioning tasks that was being trained on and evaluated on, right? This work is called All-in-One by the team over at National University of Singapore, and is a video language model designed for pre-training. It can capture video language representation from raw visual and textual signals in a very unified architecture. So all-in-one used a technique called temporal rolling operation that can capture the temporal representation of sparsely sampled frames without adding any additional parameters or increasing the time complexity. Yeah, so I included the link here if you want to dive deeper into the architecture. But the end result is that it can perform pretty well on 4 downstream video language tasks: video question answering, text to video retrieval, multiple choice QA, and visual reasoning, visual common sense reasoning. So this work is coming from a team over at Microsoft, and they focus on video recognition. And video recognition is a task quite popular in video understanding. The idea is want to identify and then categorize any objects, action items, or events happening, within a video, right? You can think of a lot of practical application of video recognition, like autonomous vehicles, security system, entertainment, etc. So Microsoft released a framework called XClip, last year. And they adapt language and image model to general video recognition. It has 2 major components. It has a cross-frame communication transformer that allows the frame to exchange information using message token. And then it has a multi-frame integration transformer that can transfer frame level representation to the video level. And additionally, XClip used the video content information themselves to enhance the text prompting using like a very video-specific prompting scheme. And despite limited label data that was trained on XClip, based on the result, it outperformed a lot of other work in 0-shot and few-shot video recognition tasks. And finally, this work called intern video is actually closest to the type of overarching video foundation model work that can do a lot of things, right? So it leveraged 2 self-supervised learning paradigms. It used mass video modeling and multimodal contrastive learning, right? And then it is some sort of cross-modal attention to derive features from these 2 transformer architecture, and then combine the results for both generative and contrastive learning. So at a high level, that how it's can combine the video representation as well as the multimodal contrastive loss part of thing. And the intern video shows a lot of promising and even outperforming a lot of other work on a video understanding benchmark that include tasks like action understanding, video language alignment, and open world video application tasks. And you can think of these tasks are some of the core abilities of any generative video perception. That's the kind of the future that we're looking at, where open world video understanding means you can just understanding in an open domain a variety of things without pre-trained on a specific task, right? So it's quite impressive what intern video was capable of. Okay, let's do a quick conclusion for my talk. So we talk about kind of intro to the foundation model. We talk about transfer learning, word embeddings, the birth of transformer and their variants. We talk a little bit about large language model, originally created with the GPT-2 model, but also with Google T5 and BERT model, right? And we highlight the importance of scaling laws and how scaling laws lead to emission abilities of large language model. We brought up the rise of large vision language model thanks to OpenAI's CLIP that leverage contrastive learning. And after that, work like Google's, like Coca from Google or Flamingo from DeepMind, all leverage contrastive learning. And then lately you see that with GPT-4, Palmy, or Cosmos from Microsoft. And then we can conclude with the new paradigm of video foundation model. And more specifically, I talk about some of the challenges of video modeling. I produced some of the work that tackle that, like VideoBird, XClip, and intern video. And actually, our team at 12 Labs has been doing a lot of research on this domain, and the core model that power our product is called Marengo, and it actually leverage a lot of the architecture innovation, training paradigm, optimization function from some of the work that I brought up. And it shows a lot of good results, right, on a lot of few shot and zero shot video language alignment tasks like video search, video retrieval, video classification, etc. Yeah, so I actually wrote a whole blog post about what I talk about here in the presentation in the link. And yeah, if you're interested, you can check it out. And we also, like, for those of you who are new to the Multimodal Weekly webinar series, we have a Discord community for folks who are interested in multimodal AI called Multimodal Minds, include a lot of practitioners, researchers, others who are working at the intersection of AI and different modalities, right? And so if you're interested, you can join the Discord, which I put the QR code here on the slide. Yeah, with that, I want to conclude my presentation and open the floor for Q&A if there's any. Thank you.
Yeah, I have a question. First off, thanks, James. That was a very in-depth history of from transformers to LLMs. That was really awesome. It was good to see. The question that I had was, in terms of 12 Labs Marengo model, it's good at identifying and tokenizing different elements in existing videos, and I've seen some really cool functionality if you're able to search through different ones. Is there any functionality for it to automatically be able to edit out based on the type of video? Let's say you upload a YouTube video from one of the big creators who makes Iron Man stuff, it's just stuff like that, they're makers. And if you want to boil that down into a YouTube short, is there a functionality to be able to I don't know, search for the sections that could be give me things that are high impact, or I don't know, a loud sound parts of the video, just when there's a boom or something. Is there a way to be able to search through those type of functionalities and slice those out programmatically?
Yeah, I mean, I can give a brief response to that, and then if anyone else from Tau Labs want to address that as well. So I think our goal as a company is to build the model under the hood, right? That can that understand video, right? And so in your example that you mentioned, video editing, video slicing is a downstream task, right? That is the consequence of understanding video, right? I think so far we offer video search as a use case because that's the first thing that is very important to understand the video. Yeah, I think we haven't do the slicing and the editing yet because I guess we haven't seen the need for us to go directly to that function yet, right? And but maybe we can think about that, if there's a need for customers or specific clients who want to use that.
Yeah, all the downstream. Sorry, go ahead, Swing.
Yeah, so actually, you bring up a really interesting point about so if you're able to understand video really well and you're able to take kind of human context, whether that's a very tangible, very specific thing of I need to find a moment where specifically this is happening, versus I think what you mentioned is more abstract. It's harder to describe. It's very contextual, right? And so I think your question comes with two parts. One is, how do you identify what is interesting from this video and give me back the timestamps of those moments, which is, I think, what our model would do. And then the second part of your question would be, how do you then take that and build out a workflow where you're actually cutting up the video? Ideally, it's probably comes with a little bit of quality edit or style that's actually something that's presentable. So the latter part we probably won't cover because that's something that our users and our customers would be building with our model and our APIs. But in terms of how can these builders actually use our model to be able to identify those contexts? So something we've noticed, one with our search, is that you can try different things. One is you can try kind of using very specific query prompts, but you could actually use abstract concepts. So if you have some topic that you want to create shorts around or videos around, whether that's part of going to be a topic of a conversation or something more visual, you can use a different kind of, you can play around with different abstraction levels and do some query engineering in a way to be able to kind of automatically get timestamps of those scenes. The other thing that we found very interesting is with the embeddings that are generated, currently our APIs only enable, like we have text to video search and classification that's up on our playground and our APIs right now. But with our embeddings, what we can actually enable is similarity search. And so if you input like you mentioned like loud sounds, but if you input some sample videos of what you want to retrieve from kind of a longer form video that you have, you'd probably be able to extract similar moments to your target videos. So I think that could also be a really interesting way for you to kind of power that use case. Does that answer your question?
It does. That's really interesting. I didn't know that you could just say, give an abstract question like, give me the interesting parts of this video, and it would still return something to you. I'll definitely play around with that a little bit. That's cool. And in terms of like the second piece, you're totally right. That's not your guys' purview. I'm actually really good at that piece, like stitching and programmatically, like creating the videos from slices. But the piece of how do you pick them, that itself has been the biggest question mark. So I'll look into seeing if this is, something interesting happens. Great, let's see that.
Yeah, so I just brought up here really quickly. I think this is a good visual representation of what So-Young just covered, and she covered it very well, but I think the visual aid will help a little bit. So here we just have some index and we are searching for something interesting. So you can see this first video here, we have it on the timeline view instead of the view by clip view, which you're probably all very familiar with. But the timeline view, I think, really illustrates what your question was getting at, which is, can we segment out all of the stuff in the larger part of the video that we might not want to edit together and really focus on the pieces that are potentially useful and then go from there. So in this context, right, it's only about a 3-minute video, but like So-Young was saying, what if I have 5 hours of raw footage and most of it is just dead frame stuff with the camera? If I just say, something interesting happens, now I'm getting my 30-second, segments that I can patch together and turn into a 45-second YouTube short or something like that. But the timeline representation here, I think, really illustrates that you can kind of do that today with the API, and you could even imagine iterating very quickly. So like So-Young was getting at with the query engineering, you could say something interesting happens or something cool happens or something wows me. You could try all these different things automatically with like a prompt generator with the API, and then pull out all the different clips that come out of them and then choose the ones that you like the best. So I'll stop there, but that's where my head went when you asked that question, which was very good, by the way.
No, that's awesome. Does it continually learn? Like if I keep asking, show me something interesting, and then if I keep querying that every single day, does it eventually get better and better, or is that subjective based on the video?
Do you mean, does it get better at the semantic understanding of what we mean when we say something interesting?
Yeah.
So that it does get better with the engine releases, right? So each kind of release of Marengo has iterations upon how well it's understanding different concepts and combining the modalities together. So it is a continual learning process in the sense that we're focusing on trying to make these improvements during each release, but it's not an online learning process, to be clear about that, right? At least not at this point. So we are collecting information, right? So you could give feedback here, which can be helpful and further fine tuning the foundation model, but it's not an online learning process at this point.
That gets back to the point of you need better prompts to be able to get better results, at least for a single.
Or I think fine tuning could also be very interesting if you have something that you're going to continue on with. You have a style, you have a topic that is a theme that will be continued to be used. I think that could also be something that could kind of help the direction of the output.
Awesome. Thanks, everyone.
Great.
Thanks for the question.
Any other question people have about? I'm curious, is there any of you here that besides Twilight people that are working on something on this topic, like either foundation models themselves as an user or as a developer? Yeah, curious to hear kind of your thoughts on the space.
Yeah, I mean, personally, I was familiar with almost all of them. I didn't know the Zwin version of from
Speech transformer, yeah.
no, I knew the Zwin. I didn't know the DeepMind version.
Oh, yeah. Receiver.
What's the name? Yeah, exactly. The receiver. For some reason I missed it. But I completely missed the entire part. I didn't know any of the video model like XClip, even the Bird video. I didn't know about him. So it was nice to discover also this part.
Yeah.
And I'm not sure, like, if you like a few months ago there was there was a project, I don't remember exactly the name, from a guy who then was hired by OpenAI, which he basically built a multimodal model that was able to combine audio, video, and yeah, audio, video, and text, and basically was able to use YouTube video to train the model. I was expecting to see it, to you to mention it, because it was at the time like for 2 weeks, as it always happened in the machine learning sphere, popular, and then it kind of disappeared. I think it was his name, like now Merlot or something like that. The icon was a glass of wine with the eyes.
Yeah. I mean, yeah. If you go further again, would love to. Would love to see it.
Yeah. In any case, I'm curious. Like today, what would be the SOTA foundational model for video understanding?
The SOTA?
The state-of-the-art model, like the GPT-4 for video.
Good question. So well, actually, I didn't see her. So our team actually just came back from this conference called CVPR, which is computer vision pattern recognition. And I'm sure, like, there's a lot of work in there that I didn't go, so I don't know. But I'm sure there's a lot of interesting stuff. But yeah, I didn't want to share it. Perspective.
Yeah, Matteo. That's a good question. And new model comes out like every 2 weeks. So it's very hard to determine like what is state of the art. But it actually, what I see is like there have been lots of foundation models coming out for like specific, trained for specific purposes. For example, some foundation models just trained for creating really good video captions. Some is really good at retrieval. Those type of different foundation models, right? So for example, Google's Video Coca is considered as one of the state-of-the-art model right now that covers most of the task for videos. Vid2Sick is another model that generates really dense descriptions from videos. And intern video is another good one. James, I think that already mentioned. So there aren't lots of video foundation models coming out like every day, every week, unlike image foundation models. But we see these trends increasing, and we expect more models to come out soon.
Okay, cool. Yeah. I guess until OpenAI will release GPT-5 and will destroy the industry once again. It was kind of funny. I mean, funny was to a certain extent funny to see all the NLP researcher basically going crazy on Twitter because all their years of research was basically be kind of useless after GPT-4.
Right. Yeah. So 12 Labs, we also built our own foundation model, but we didn't release any blog article or technical papers about it. But we will be doing that soon. So keep us posted.
Oh,
Yeah.
wow.
Are you talking about Waymark? Were you talking about Waymark? The video, the video, the ChatGPT version that you said, is it Waymark?
No, I think it was Merlot or something like that.
Oh,
Let
Melo.
me-
I know Melo. Yeah, give me 1 second.
Yeah, I think the work came from AI2.
Let me
Yeah.
see.
They also released a second version very recently.
Yeah, but I do heard of Waymark though. I think is that Mary, is that the video generation talking head or something?
They do, well, it's not so accurate. I tried it. They use AI to generate commercial ad video. So you basically, I tried to do something for my sister. I put North Cyprus real estate and, just added name of a couple of city. That one came up good. It did actually good. It created a nice ad, visual, videos, everything. But then I tried something else and then totally gave me something different. So,
Yeah. Yeah, I mean, yeah, I think that's what you mentioned about video generation, right? Text to video generation.
yes.
Um,
Yes.
Yeah, I mean, so that's actually like a whole nother domain of video research that I think is also pretty exciting, right? Like generating net new video from scratch, right? There's companies are doing this like Runway, Synthesia, just to name a few, and even Waymark is deploy. I think
I use Runway a lot.
yeah, I mean it's a good product. I mean a lot of excitement for sure. I think I think like there's definitely like room to grow in terms of the quality control and the thing that I'm sure like to your point, getting the exact file grain generation that satisfy like certain user needs is definitely like still a long way to go. But I'm definitely excited to see like the work coming from those teams because that in general, first of all, it drive more interest for video AI, kind of benefit a lot of work from our team to lab, but also like a lot of people who do research on this. And secondly, it create like more training data, right? Like for people to train their model on, right? So yeah, we're not gonna run out of any training data soon for video. So
Well, I'm
exciting.
I'm very interested in your model. I'd like to see where it goes because I'm looking for something like yours to use the API so we can integrate it in our platform. It has a lot of use for content creators.
Mm-hmm. Yeah, yeah. I mean, yeah. Feel free to let us know if you run into any problem with the process of like trying out the product. And yeah, like our Discord is there, and then some of our team members is also like pretty active in terms of getting feedback. So yeah, love to get your feedback on the product. Then
Okay.
hopefully, yeah, benefit your use cases.
Thank you.
Yeah. Awesome. So it's 2:38. So I think we're running a little bit over time, but thanks everyone for participating in the session. There's a recording that will be available on YouTube sometime next week that will release. And if you want to go back and then watch my presentation or have any further question, feel free to reach out. And then as I mentioned in the beginning, we do this webinar session weekly every Friday. So next week we'll have couple of speakers that will go in and talk about like multimodal AI, which is going to be pretty exciting as well. So yeah, stay tuned and hope to see you again next week. Cheers.
Thanks, James. See you next week.
Everyone.
Thank you.
Thank you, everyone.
Everybody, take care. Bye.